All right, guys, this is 5.1 for statistics, and we're going to be talking about probabilities again in this chapter. We're going to go a little bit further in, as was just, hey, here's how we find the probability, but more into how can we kind of use these probabilities to predict more things for us. So the first thing that we're going to do is introduce a few new vocabulary terms here. So random variable, you've probably heard this quite a bit in the past. So in these contexts, we're going to use x as the random variable we're going to get. So you get some value out of it. It's always going to be a quantitative variable, meaning it's going to be a number, right, as opposed to a like yes or no or color or category kind of response there. Um, so these can either be categorized as discrete or continuous. If it is discrete, there is a finite number of these which you can get, right? So I'd say, well, the number of students in a particular classroom, right? It's either going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up through 30, 40, whatever, right? It can't, there's not an infinite number of kids who could be in a particular like classroom, right? But if I were to do anything like, how long does it take me to brush my teeth, right? Depending on how I measure that, right, I could go down to milliseconds and microseconds and that. So there's an infinite number of different times which I could get, right? So I could go, well, I rushed for 3 minutes and 45.721 seconds, I mean, like that, right? So continuous means it's going to be, you could get any possible number out of it, whereas a discrete is much more of it's this or this or this. Think kind of you're counting by like whole number stuff versus decimals and any kind of possible decimal you could get for it. So go ahead and try out A, B, C, and D here and say, well, would that be continuous or would that be discrete? And then come back. All right, so we should get continuous for the first one because the time it takes a student to register for a college class, again, that time can be measured in any number of decimals, so we could make that as continuous as we wanted to. The number of bad checks that are cashed in a day in a bank, there's going to be a finite number of those. You're not going to be getting an infinite number of decimals and things of that nature. Amount of gas needed to drive so many miles, well, it depends on your vehicle, and you can measure that gas in gallons or liters or fractions of gallons and decimals of liters and whatever you need, right? And then finally, the number of people that voted in a district, well, that's going to be discrete once again because it's either 1, 2, 3, 4 people, right? It's not 78.21 people voted. That doesn't make sense. So it's not going to be continuous. It's going to be discrete there. All right, so probability distributions are what we're going to be looking at quite a bit this chapter. They look kind of like this, so it's kind of like a histogram in a sense, right? So here's the outcomes that I'm looking at, right? So an outcome of 0, an outcome of 1, 2, 3, 4, 5, 6. Those are the variables, right? That's what the people scored on their exam. So I had 1,400 score a 0, 2,600 score 1, and so forth, right? And then I said, well, what's the probabilities there? Well, the probability of someone scoring a 0 is 1,400 out of the total, right? So I just take the number divided by the total, which again is how we've been doing probabilities for quite some time, and then I get the probability here, right, as a decimal. And then when I do my histogram, I connect all of those and I can hopefully see a pattern, right? See, hey, most people are kind of in this range here. It has a pretty steep drop off as you go higher, but then a fairly more gradual one as you go lower. So that tells me some things about this like test and how people are doing on it that I might care about or want to use. All right, so let's talk about discrete probability distributions. This is one of my favorite data points that I've gotten, and it is the frequency of letters being used in the English language. So we get this by taking 1,000 words out of crossword puzzles and then counting up how many times we see each of these different letters, right? And that tells us, well, what's the probability of a letter a occurring and stuff. So this would be a useful strategy for like hangman or wheel of fortune stuff like like that, right? So I've given you the frequencies and some of the probabilities. What I want you to do is find the the probabilities for the ones I have not given you. Spoilers, since there's 1,000 letters as our sample, you're just taking that number, dividing it by 1,000. All that really does is just move over the decimal point a few places. So go ahead and fill out that, and then answer questions B and C, and then come back here. All right, so on B, all of these probabilities would have to add up to be 1, right? Because every single letter in the English language is there, so the probability of you getting a letter in the English language is 100% because we're only looking at letters in the English language, right? So then if I want to figure, hey, what's my probability of getting a vowel, right? I just take all of my vowels, so my A, my E, my I, my O, and my U. I add all of those up. I get about 0.38, seeing that, hey, a little over a third of my letters end up being vowels, which is why vowels are so common for us, right? There's 5 letters that are a third of all of the letters used. So, and a few quick little side notes that I always find kind of interesting here is people like think about like what letters are common and what letters aren't. And the least common letter here is J. People always think that J is way more common than it is. It's really not that common. And I think where you get mixed up on is that J is a decently common first letter in a word, but it doesn't occur very often inside of a word, if that makes sense. So like a letter like Z or X, again, those are uncommon, but they occur more often inside of words, right? So like there's not very many words that start with an X, but a decent number of like words have X's inside of them still. Whereas J is the kind of opposite, where like there's a lot of proper nouns which have a J to like start, but very few words have J's inside of them. It's just kind of a cool thing that I wanted to point out because I always kind of find that fascinating. Okay, so this is what's called expected value, and this is a really common thing to kind of do here. So the technical term is the mean of a discrete population probability distribution. So you can kind of see why we don't like saying that mouthful every single time. So it's commonly called the expected value because that's effectively what it tells you, right? So we use the variable mu because that's kind of what it is, right? It's the mean. So we take the outcome times the probability of that outcome, and we do that for every single one of those, right? So this is only going to work for numerical things, so we like couldn't use it here for like letters because A is not a numerical outcome, so I couldn't say, well, A times 0.085, right? But if it's a number, I can. So a really easy way to look at this, let me get my camera out, is if I look at rolling a 6-sided die, what's my expected value or my average outcome when I roll a die, right? Well, I take the outcome times the probability of that outcome, and I do that for every single possible outcome, then add them all up. So I would say my first outcome is I roll a 1 times the probability, which is 1/6, plus my second outcome is a 2 times my probability, which is 1/6, plus my third outcome is a 3 times 1/6, and then plus 4 times 1/6, and then plus 5 times 1/6, and then plus 6 times 1/6. Right? And I can just go and say, well, let's add all of those up. Right? So 1 times 1/6 is just 1/6, so I don't really need to do much else there. 6 plus 2/6, because 2 times 1/6 is 2/6. I hope you can see that pattern there. Plus 3/6 plus 4/6 plus 5/6 plus 6/6, which is also called 1. Right? Add all that up, and I get 7.5, which as a decimal is 3.5. So that equals 3.5. So 3.5 is what I would call my expected value when I roll a single 6-sided die. Now that seems really dumb, right? It seems like, well, you can't roll a 3.5. Why would you expect to roll a 3.5? And again, in this context, it's the whole average problem, right? Your average roll is a 3.5, right? So if you had to, let's say I was going to pay you based off of what your roll was, right? And every day you would roll a 6-sided die, and if you rolled a 1, I'd pay you $1, right? The next day you roll it, you roll a 5, I pay you $5, right? And you do that every single day, right? Your average earnings per day would be $3.5. That's effectively what this means. You're going to expect an average of $3.5 every time, right? It doesn't mean you're going to get exactly $3.5 every time, but your average over a long period of time would be 3.5 per payment, if that makes sense. So this is a very strong and powerful thing for us to have, and we're going to use this quite a bit, right? Then we look at the standard deviation for this type of situation. This equation is a little bit messy, especially when you have to do it by hand. So if I wanted to find the standard deviation of that distribution I just did, right, I want to sum up every single value of x minus the mu to the second power times the probability. And then I want to square root it, right? So I would do 1 minus 3.5 and then square it times 1/6 plus 2 minus 3.5 and then square it times 1/6 all the way up to 6 minus 3.5 and then square it times 1/6 and then add up all of those and then square root them to get my standard deviation, right? So I give you that equation, but this is not a thing that I'm going to have you be calculating by hand very much, if at all. So I'm not going to stress that all that much here. Okay. All right. Where's my cursor? There it is. Okay. So let's go ahead and try this idea out. Right. So go ahead and read through the situation here, then pause, read through it, answer those questions as best as you can, then come back here and we will go through them. All right, so this is an example of a very, very basic casino game, okay, where you're going to be kind of betting on the outcome of it, and then you're going to be paid based off of what the outcome is. So this is, think of our project from last chapter. It's that idea, but this is going to be a little bit more of a there's more than just a win-loss state. There's different levels of win state. So that's the big change, which we couldn't do then, but now we can do now because of this, right? So my outcomes are either 0, 1, 2, or $3. That's what I can get, right? So the ways that I can get those outcomes, and if you do a tree diagram, this is a fairly easy thing to get. I either get 3 zeros, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, or 1, 1, 1, right? But really the order doesn't matter here. So I can really categorize my 0, 0, 1, 0, 1, 0, and 1, 0, 0. All those are effectively the same outcome for me. Those are all getting $1, right? And then 0, 1, 1, 1, 0, 1, and 1, 1, 0 are all just the same outcome of me getting $2, right? And then there's only one way for me to get all 3 and one way for me to get all zeros, right? So the frequencies, this can only happen once, this happens 3, 3, and 1. So then to get the probability, well, that's 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. So then I get these as my probabilities. So then to find my expected value, I just take all of these the outcome times the probability. Well, 0 times the thing is going to be 0. 1 times that is just itself. 2 times that is just going to be 0.75. And then 3 times that is going to be 0.375. Right? So then if I add up all of those, like I just did on that dice egg example, I get 1.5, which means that I would expect playing this game to win $1.50 every single time that I play. Right? So then if I'm the casino or the person running the game, each person who plays it, I'm going to expect to make about 50 cents because they're paying me $2 to play, and on average, I'm going to pay out $1.50, right? So if we do that, so it may feel bad in a very short run, right? So if I only have 5 people play, there's a decent chance that I end up paying out more than I make and I lose money. But if I have this playing for 100, 200, 300 people come and play my game, over the course of that time, if I have 100 people play and I'm making 50 cents per person, I just made $50, right? So that's how casinos make money, is stuff like this. It's little margins. I'm going to make 50 cents off of every play. Or in slot machines and stuff, they'll make, if someone plays a $1 game, they'll end up making maybe 5 cents for every dollar bet. That seems like not a whole lot of money, but over time, you got 1 million people playing slots multiple times. 5 cents for every time played adds up pretty darn fast. So that's how those kind of things end up working. All right. So that is it for chapter for 5.1. So here's our homework for it, 1 through 6, and then we're going to be doing 7 through 17, just the odds. And we'll talk to you guys next time.